Welcome, everyone. Today we'll be hearing from Stephan, and you are free to take it away. You have 50 minutes. If you want to ask for time, I'll let you know how much time you have left, but I won't be holding up any signs.
I see. Thank you. Yeah, I put a clock here. 50 minutes is perfect. Thank you. It's great to see all of you. I've seen many of you already because I watched recordings, but we have our own theory seminar at the same time. Okay, so the paper I'm presenting is joint work with Usher, and it's combining auction theory and search theory. Okay, so let me share my slides. So I think that should work. Does everyone see the slides? Okay, is the sound okay? Perfect. Okay, so it's joint work with Usher on auctions with frictions. And so I was teaching auction theory last semester. And so here's a standard auction theory model, right? So there's a seller who owns an indivisible object. There are n buyers who have private values for the object from V1 to Vn, okay? And so the textbook I was using was Putting Auction Theory to Work by Paul Milgram. And so here's a little question to start. So at the beginning of his textbook, he claims there's one specific issue. That is, he says, one of the biggest factors for the success of an auction from the viewpoint of a seller. So when selling an object with an auction, says, here's the one thing that's really important. Okay, so question, what is that? So is it the reserve price? Is it the auction format, first price versus second price auction? Well, so according to him, it's finding bidders. So I thought you would like that. And actually motivating them to participate. So he writes, marketing a sale is often the biggest factor in the success. And then he goes on and says, bidders actually may need to study the opportunity and line up partners, financing, regulatory approvals, and so on. So bidders can actually be hard to motivate because they're cost of participation, okay? So the idea here is when you run an auction, they're not just n bidders waiting eagerly to bid in your auction. Instead, you have to market, you have to find these bidders, and you have to motivate them to participate because it's actually costly for the bidders to do so. Okay, because they need to study the opportunity, they need to learn about the value. So, so in another word, what we want to do in order to think about this biggest factor in the success of an auction is to think about an auction in which the auctioneer has to search for bidders. Okay, and for the insiders, it's basically a simultaneous search model. Good. So, so what we want to do is we'll look at an auction, otherwise standard, one seller, indivisible objects, private values. But instead of the n being something exogenously given, we'll think about the n as being endogenously determined and jointly by the seller's costly recruitment effort. So this costly recruitment effort, that will be sort of our translation of marketing the sale, and the buyer's costly entry. So in the model, the buyers will have to acquire a signal to learn about their value. That's sort of modeling this cost to study the opportunity. Okay. So the main trade-off here is going to be from the seller's point of view when he thinks about recruiting more bidders. Well, recruiting more bidders increases competition. So the bidders will behave more competitively. So that's good. And in addition, there's a second reason. You have a higher probability of sampling a buyer with a high value, right? On the other hand, if the bidders anticipate that there's more recruitment, it can be harder to motivate the bidders to participate and actually to invest to study the opportunity. Okay. And this can be a vicious cycle. So the seller can sort of recruit more and more bidders, and the bidders on the other side become more and more cautious to enter. And we'll see that will result in excessive sort of recruitment activities, inefficiencies, and can even lead to market breakdown. Okay.
Stephan, question here. So I think one of the main kind of devices that an auctioneer has to recruit bidders is to change the auction format. And some auction formats might be more conducive to bidding than others. Some might be more risky than others. And so the way I understand it and the way you want probably to set it up is that the auction format is given in your situation. But if you want to really think about is how you could apply this to kind of real world, I don't know, spectrum auctions or other type of auctions, would be that the auction format is actually endogenous, and that this might also determine how many bidders there are.
Okay, so there are multiple things that you said. So the auction format will matter, and we'll discuss how the auction format matters. Here, I want to think about it's costly to contact bidders, to tell them, here's an auction that I'm running. That's sort of what I'm thinking about. And more generally, so the way I'm thinking about it is really not so much about the FCC running a spectrum auction. So what I'm thinking about is sort of more informal settings, where we think about the auction as reflecting some version of price competition. Okay, so it's more IO-ish. So we can think about selling a house. When you're selling a house, you presumably take the best offer. Okay, so there's a form of price competition, but it's not a formal auction in the sense that the seller of a house doesn't necessarily have all the commitment power that the government would have when running, for example, a procurement auction. Okay, so what we want to think about is a setting where the seller has limited commitment power, and in particular, we're not looking at what is the optimal mechanism to run here. Okay, but we'll talk about it later, and there are going to be some implications for optimal mechanisms and what type of auction formats will be good or bad, and we'll talk about that as well. Okay.
Okay.
So Stephan, in the examples that you're giving, they're selling substitute goods, like the sellers are substitutes for each other from the buyer's perspective. Should I be thinking that?
Yeah, you should. There's only one person selling a house in my world.
Okay. Okay, maybe you'll come back to that at the end.
Yeah. Good. Okay, fine. So here's the model. So we're really thinking about sort of like an auction, setting. So there's one seller who owns an indivisible object, and he will choose a recruitment effort X that will translate into a stochastic number of bidders that are contacted. And an effort X comes at a cost X times S, this is strictly positive, and the number of contacted bidders is going to be Poisson distributed with mean X. So what it means is, if you put in more effort, there are more bidders, but you're not perfectly controlling the number of bidders, and increasing the expected number of bidders by 1 comes at a cost of S. Okay? Okay, so that's the first stage. The seller chooses how much effort to invest into recruiting bidders. That's marketing. Second stage, the contacted bidders will decide whether to participate or not. And if they participate, this comes at a cost C. If a bidder decides to participate, then she'll learn the number of other participants, so the number of participants little n, and also the true value of the object to herself. So this will be her private value V drawn from some distribution G. Okay. And in that last stage, all the bidders who are participating then submit bids. The highest bidder wins and pays her bid. Okay, so it's a first price auction in the last stage. And then the payoffs are for the seller. If the winning bid is P minus the recruitment cost X times S. And for the bidders, it's V minus P minus C if the bidder is winning, minus C if the bidder is losing, and 0 if the bidder is not participating. So not participating is better than participating and losing, of course. That's going to be important. Okay, so to have one story in mind, the seller may advertise an auction, it's some auction site, Friday at 12. And then the bidders have to decide whether to travel there or not at some cost C. When they travel there, they learn how many bidders there are in total, the little m, and they learn their own private value, little v. Okay, so they get a more precise signal. Good.
Stephan,
so that's yes?
Quick question. So the bidders do observe X or not?
Very good. That's going to be critical. No, the recruitment effort is going to be unobservable. Okay, so I get a call. Are you interested? Maybe the person tries to convince me that I'm the only one he's calling and says, especially for you, but I don't know whether to trust it. Okay, so I don't know. I do not. So X is unobservable. Okay, that's the point.
Related question. So N is observed by bidders before bidding.
Yes.
Have you thought what happens if N is unobserved?
Yes. So so here we'll assume that the bidders know exactly against how many other bidders they're bidding, And you may think that in many of the settings that we have in mind, like informal auctions, it's actually not so clear how many bidders there are. And the seller cannot really credibly commit to revealing that. And we'll talk about that. But the simpler case is where the bidders know the number of other bidders. So we'll start with the simpler case.
And did you look also at what is optimal from the seller's perspective to say if he can announce N or cannot announce N, whether he would like to do that or?
Yeah, we'll have something about that.
Okay.
So we can say sort of what are exactly. Okay, so okay, so the basics. So this is a 3-stage game, if you like, right? And we're going to solve it from the back. So last stage is going to be a bidding stage in the first price auction. So last stage, everyone knows how many people there are, knows their own value. They submit bids. It's a first price auction, and we're going to find out what is the bidding strategy. So beta of v comma n is the bidding bid of a buyer with value v when there are n bidders in total. Okay, so that's the bidding strategy on the last stage. The second stage is the entry stage. The bidders have to decide whether or not to enter. And they will enter with some probability q between 0 and 1. Okay. So at the entry stage, all the bidders for now are equal. So bidder doesn't know much, just gets a call. Bidder has an expectation about these things, but doesn't know much. So all we know is, yes or no, that's the question. So that's an entry probability q. And then the first stage is the recruitment choice, X. So how much effort to invest into recruiting bidders. Okay, and that's therefore we're going to solve from the back. Okay, so seller chooses how much effort. The effort is unobservable, but of course the bidders have an equilibrium conjecture, right? Then the bidders decide whether to participate, yes or no, partly based on their conjecture about how many other bidders there are. Then they learn how many bidders there are in total, because in this version we look at the observable case, and then they submit bids in the first price auction. Okay. And the basic point here is what we want to do is a simple model in which, we'll have recruitment effort by the seller, and we have this costly, entry decision by the bidders. Okay. And basically, also to guide you towards where you want to go, it's going to be harder to motivate bidders when bidders anticipate that there are more other bidders who want to participate. Okay. So that's the main trade-off. So, okay, so there were already quite a few questions. I have questions here on the bottom of the slide, so, feel free if you have more questions.
Stephan, can I ask, I'm pretty sure someone already questioned this one, but in number 3 there, it looks like the bidder only knows her value after she's decided whether to join.
Yes.
Probably someone raised that one, but it seems a little special.
Yeah, so in general, so this is sort of the value updating model. So Hendricks and Al, for example, have a paper on offshore oil rigs and stuff. And so you have to invest something to learn about the geography and everything. And this signal is costly. And before you acquire the signal, you have no further information than anyone else. That's the model. We do have a variation in which we allow bidders to be a little bit more heterogeneous. Okay, so that's what you're asking. So here, bidders, when they get a call, they're all the same. That makes things easy. And then we can think about bidders having some private information ex ante, lots of things happen. Okay.
So Stephan, you didn't do literature. I mean, there's quite a lot on participation decisions. Is the newest thing here the solicitation? Or? Yeah,
I think that so that's true. So there's a lot of literature on sort of bidders' entry costs and participation costs, both from the perspective of obviously optimal design, entry fees, and so on. So here it's a combination of the seller has to invest effort to recruit bidders, and the bidders, have to invest entry cost, and we'll look at the combination of these two things in a setting in which the seller cannot commit. Okay. And there will be a slide with the relation to the literature. Yeah.
Can I also ask something?
Yeah.
In the sense that it seems that could you also accommodate some part of common values? Because some of the stuff is exactly, you really, if I see more bidders enter there, it should be good news somehow, yes. No?
Yeah, common values. So many of your questions are about sort of variations that we actually cover. So I'm glad about these things. So common values is something that we'll discuss later. Okay. Another thing that you mentioned was a little bit heterogeneity. Whether, what happens if the number of bidders, the little n is not observable. So we'll discuss that one at a time. Okay. Okay, so basic idea, the seller and the bidders together jointly determine the number of bidders that are actually in the auction. Okay, good. So we'll start from the back. So last stage is the bidding stage. So we'll determine the beta. And then we'll go back and study the participation stage, determine the Q, and then we'll go one back and study the recruitment choice of the seller, the X. Okay, that's the roadmap here. Okay, last stage, auction. So at the auction stage, you learn how many bidders there are in total, the little n, and you learn your own value V. Okay. So paying cost C, you get a signal that gives you your value V. And that stage, then you're bidding, and really this is a standard first price private value auction. And also in the textbook by Paul Milgram, it's this first price auction has a unique symmetric equilibrium. Let's denote this by beta FPA. Okay. So beta FPA, the bidding strategy has a few natural properties reflecting price competition, which is really what we want to capture here. So beta FPA of V, N is always smaller than V. So there's always some bid shading. So bidders always have some market power because there's a chance all the others have low values. If a bidder is the only bidder, the bidder bids the monopoly price, which is 0. Beta is increasing in N. So the more other bidders there are, the more competition there are. So that's like a oligopoly. And as N becomes large, the bids are increasing to the true value. So bidders in the limit behave perfectly competitive. And these are the properties that we want to use. Okay? Very natural properties of price competition, that's what we want to use. Running example, if the value is uniformly distributed between 0 and 1, then beta FPA is equal to n minus 1 over n times V. And that has the properties I just mentioned. Okay, so I will use the uniform distribution quite often as an example. Okay, so we've solved the auction stage. We've solved completely the last stage. That was easy. So let's go one step.
Was there a reason to go with first price rather than second price?
I will talk about the auction format. So in my view, first price auction is more natural. If you think about sort of informal competition, you take the best offer. But we'll talk about the second price auction.
Okay.
Stephan, I think you are going to talk about this. It's just I just want to know what's going to come. Yeah. So in this kind of problem with private values, actually normally it doesn't really matter whether bidders observe the number of other bidders.
Yep.
And also it also doesn't really matter as long as you use the standard auction. So I mean, are you going to talk about some differences across this?
Yes. Yes.
Okay.
Yeah, very good. So exactly. So there will be some versions of revenue equivalence under some conditions, but not always. So we have to be a little bit careful. But the simple model is simple. So okay. So last stage is a simple first price auction, and there are going to be revenue equivalence. Good. Last stage we solved. Second to last stage is the entry stage. The bidders don't observe X, but they have a equilibrium conjecture about it. So if they expect X, and they expect other bidders to participate with probability Q, then the expected number of other participants is X times Q, which we'll denote by lambda, the participation level. Okay. And the actual number of participants is going to be Poisson distributed with mean lambda. Okay. That's one of the nice features of the Poisson distribution. So given the expected number of other participants, lambda, and given how they bid the beta FPA, I can calculate as a bidder, what is my expected utility from entry? Let's denote this by U of lambda. And an immediate implication of the properties that we just had is that U of lambda is decreasing in lambda. And as lambda goes to infinity, U of lambda goes to 0. That's because there are more bidders, so I have a smaller probability of winning, and the others are also bidding more aggressively. Okay, so if there are too many other bidders, I definitely don't want to participate because U of lambda at some point is going to be smaller than the C, the entry costs. We'll assume that on the other side, if I know I'm the only bidder, U of 0 is larger than C. So I definitely want to enter if there's no one else. And in the middle, there's going to be some break-even participation level lambda B max, at which a bidder is just indifferent. The expected utility at lambda B max is equal to the entry cost C. And that gives an easy way to characterize the entry stage. Right? The bidders expect less than a lambda B max participation. If lambda is below lambda B max, then every bidder will want to participate. If lambda is equal to lambda v max, bidders are indifferent, they are willing to mix. And if lambda is larger than lambda v max, the bidders have a strict incentive not to participate, and Q must be equal to 0. So the entry stage is completely characterized by lambda v max, the bidders break even participation level. So we've solved the second stage.
Sorry,
yeah.
Stephan. So here lambda relies on the conjecture on other bidders, and the Q on the right-hand side is my own Q.
No. It's the participation probability by the other bidders. I expect lambda other bidders to be contacted. I expect X other bidders to be contacted. Each bidder participates with probably Q. So X times Q is the expected number of other bidders who are also participating.
That's right, but the best response is by me, because of course Q is inside lambda.
Yep.
So, okay.
So below what you see is sort of the equilibrium fixed point condition. So it says.
That's right. So what basically the column on the right is basically my best response to the other Q, which is everybody else.
Exactly. Okay. Thank you. That was important. Yes. Okay. So this is sort of the equilibrium condition. So Q is in equilibrium if the implied lambda. Okay. So I said uniform example. So in the uniform example, U of lambda, well, U of lambda is decreasing. Here, U of 0, of course, is a half, right? With the uniform distribution of the values. There are two cases which I want to use. So U of 2 is about 0.15. So this means if the entry cost is 0.15, the break-even level for the bidders is about 2. And at 0.14, so the bidders break-even level is at around 5. Okay, so of course, the lower is the entry cost, the more bidders are willing to enter. Okay, so that's the entry stage. That's good. Questions? So now the recruitment stage. Okay, so given the bidders' bidding behavior beta FBA, and given a participation level lambda, we can calculate the seller's expected revenue R of lambda. Natural implication of what we just observed is that R of lambda is increasing in lambda, R of 0 is 0, and R of lambda goes to 1 as lambda becomes large. Because I assumed the values are from the unit interval.
Stephan, I wanted to ask, I think before, but so I guess you have potential bidders are infinitely many, so they do not learn anything from having become one of the contacted ones. Mm-hmm. That's correct, right? So there's no learning. I don't know. I cannot infer anything about X from the fact that I was contacted.
Yeah. So here you cannot learn anything from the fact that you're contacted about the expected number of other bidders, and that's sort of a property of the Poisson distribution that makes things easier. Okay. In principle, one could. Yeah. We'll actually have a version in which being contacted will contain information. So for example, you're not quite sure how many people are contacted, then being contacted contains information, but let's not get there. For now, you don't update based on being there. Any other questions? Okay, so given the bidding strategy, given the expected given for any given participation level lambda, we can calculate the seller's expected revenue R of lambda. R of lambda is increasing, and there are two reasons why it's increasing, and that's important. So first, there's a higher chance of having a high value bidder, so higher V translates into higher bid. And second, if there are more bidders, they're going to be bid more aggressively. So for every V, the bid is going to be higher. Okay. So if the seller chooses a particular participation level lambda by choosing a recruitment effort X equal to lambda over Q, the profit of the seller is R of lambda revenue minus the cost of generating participation level lambda, which is lambda times S over Q, where S over Q is the cost per participating bidder. So Q is the probability a bidder participates, and the smaller is Q, the more bidders you have to contact in order to generate a given level lambda, right? So S over Q is like an equilibrium cost, because the Q is an equilibrium object. Now, for an interior equilibrium, the necessary first order condition is that marginal revenue has to be equal to marginal cost. So R prime of lambda has to be equal to the equilibrium cost of the bidder, S over Q. Okay. Everything is fine. And the first little subtlety here is going to be that profit is not concave. So, so the necessary first order condition is not sufficient. In fact, we may have a corner solution when the search costs or recruitment costs S are high. So let me show you. So if the search costs S over Q are above some level, the break-even cost of the seller S max, then the seller will optimally choose to recruit no one. If S over Q is below the break-even level, the seller will choose a level lambda S at which marginal revenue is equal to marginal cost. And this lambda S has to be larger than a minimal scale. Okay, so let me show you that. Take a picture which you've seen before from intermediate micro. So here what you see in blue is the marginal revenue curve, first increasing, then decreasing. That's the non-concavity. And what you also see is the average revenue curve here. Okay, average revenue curve, the revenue per bidder. Okay, and you see the average revenue curve is maximal where the average revenue curve crosses the marginal revenue curve, or vice versa. Okay. So if the recruitment cost S over Q is in this picture above 0.14, that's the seller's break-even cost, the seller will optimally choose to recruit no one because the cost per bidder S over Q is larger than the average revenue per bidder. It's clear. If the cost is below this level, then the seller will recruit some bidders, and he will always choose a number of bidders that's to the right of this intersection, right? That's above the minimal scale. So either corner solutions or a strictly positive number above the minimal scale. Good.
So you chose to have this issue, right? Because you, if you assume that the cost was quadratic or something, you won't have this problem. I mean, this problem. You won't have this corner solution.
If it's quadratic, I don't know what happens with quadratic.
X squared times S.
But I'm not sure. Are you sure?
No, I mean, but not my paper, so I don't have to be sure.
Okay, so I don't know what happens with quadratic cost.
Q something, I don't know. So if you make...
But the main thing is the marginal cost when the effort is 0. If the marginal cost is 0, like in the quadratic case, then you have incentive too.
That's correct. That's what I had in mind.
Yeah,
but,
something.
But the, in equilibrium,
also the
right?
marginal revenue is 0, so I don't know.
So in equilibrium, Q is going to be, such that you actually don't have the boundary solution. Is that what you're going to get?
Sorry?
No, in equilibrium, the Q.
Yeah.
No, here, you take Q as given, right? So I mean, look, when you think about the seller's problem, but Q has to be determined in equilibrium.
Yeah, sure.
So then, you are not going to have the, the corner solution. Is that what you're going to get? Or?
So here we're just looking at what the seller would optimally do given Q, and then, as we said, later we'll determine the Q. Exactly. And sort of, so I don't know. So the way I understand Sandro is sort of, so the linear case or a roughly linear case is special. I would have to think about sort of what is exactly the condition that you need, because margin revenue also goes to 0, right? At 0. So you need some condition on the slope, but sure, you can find a condition where you don't have a corner solution. Very good. So, so what's important here for the seller's part recruitment is the two numbers, the break-even cost as max, which is at 0.14 here, and the minimal scale, which is at 2.6. Okay, in the example with the uniform distribution for which I calculated this picture. Okay, in general, there will always be a break-even cost and a minimal scale given the linear recruitment cost. Good. So now we have solved everything, I think. So we've the last stage, the bidding stage, the beta FPA. The entry stage was given by the bidder's break-even level, and the seller's recruitment cost. If the seller recruits anyone, its marginal benefits equal to marginal cost, but it might be a corner solution depending on whether the costs are above or below the break-even cost. And if the seller recruits anyone, it's above the minimal scale. It's like the standard case from production. Okay. So then, principle, we're ready to have an equilibrium definition, right? Equilibrium is a lambda star, a recruitment choice, a belief of the bidders about how many other bidders participate. On equilibrium belief must be correct. The entry stage decision Q star must be optimal, so satisfy the equilibrium condition that I showed you before, and the bidding behavior has to be mutually optimal, which we know has to mean that the bidding strategy is equal to the unique equilibrium of the first price auction beta FPA. Good. and there's a small off-path event where I don't expect anyone to be recruited. And if I'm recruited, I have to have some belief about how many other bidders there are. Okay. So we also take care of this in the paper or in the draft. Good. So here's the first little result. It's about market breakdown. If lambda B max, the bidder's break-even level, is below lambda S min, the seller's minimal scale, then there is no trade in any equilibrium for any level of the solicitation cost. So whatever is the solicitation cost will not have trade. In the uniform example, if the entry cost of the bidders are 0.15, then the bidder's break-even level is 2. I said before the seller's minimal scale is at 2.6. So the minimal scale is above the bidder's break-even level. So there can be no trade for any level of the sampling costs. Okay. So what's going on here is the seller would like to commit to recruit only lambda B max bidders or fewer of them. The bidders would be happy to participate. However, once the bidders are participating, the seller has an incentive to recruit more than lambda S min bidders because we will always recruit more than the minimal scale. And the bidders anticipate that. And so they can't, they will not participate. Okay, so it's a very simple observation. It follows directly from these simple observations that we had before. And it illustrates just the power here of the lack of commitment by the seller. The seller would like to commit, cannot commit, and because he cannot commit, will have excessive recruitment, and that precludes trade. And it precludes trade even if the recruitment itself is cheap. Okay. That was. So are there questions about that?
So this result may rely on the linear effort cost function, I guess, right?
I'm sure that sort of, as Sandro said, so we'll be able to find something where we don't have the minimal scale.
Yeah.
I mean, basically, yeah.
And when this condition holds, is it is it when the C is sufficiently small? This condition, the lambda max B is less than lambda mean S.
If C is sufficiently large, right?
C is sufficiently large.
Right. So large C means small lambda V max.
I see.
So,
yeah.
so you were able to subsidize.
Very good. So we're thinking about optimal design.
Right, just maybe with the subsidy. Well, I don't think the auction format should. But
exactly. So very good. So subsidy. The seller would like to get bidders to participate, so pay a subsidy. A subsidy, could help you for two reasons. It could be that, when you pay a subsidy to a bidder, it's actually costly to get bidders, because you have to pay every bidder. Okay. Right. So it's like money burning. So this by itself doesn't help because we already said for any S, you don't want to, you don't get any trade. However, what helps is that if you have a subsidy, it effectively reduces the C, the entry costs. And by reducing the entry costs, you get lambda higher than lambda S min. Okay, so that's how a subsidy helps. The problem with a subsidy is that, well, if I give you $1,000, if you look at my house, many people may show up. Okay, so that's.
Yeah, the subsidy has to be less than C, right?
Right.
What is your conjecture? If you have the optimal subsidy, which is probably less than this C,
yeah,
you still have this potential breakdown with the optimal subsidy?
No.
No.
No, wait a second. So I think yesterday I was thinking long about the subsidies, and I think it's
okay.
So we have some results on subsidies and what is the optimal level of the subsidy. Actually, what I find interesting is often you want to ask for an entry fee from the bidders, but often you can't pay subsidies. Then
right.
Okay.
Right, that's true, but I was just curious. Thanks.
So more generally, we're going to have results of the type, there's going to be an inefficiency. And so it's natural to think about, so given there's an inefficiency, it really means there's money left on the table, right? And there should be incentives to think about, okay, so how do we get this money up, to us into our pockets? And so here, Gabor suggested one way, which is a subsidy, and there will be other ways, for later inefficiencies as well.
But so just so that I'm following, it's more about the inability to commit, right? So if you were to be given any other tool that you could commit to in some meaningful way, there would probably be a way of unraveling this, right? right? Like this is the idea that lack of commitment means the auctioneer can't bring in people. Am I interpreting that correctly?
Yeah, so here it's sort of, you can't help yourself but recruit too many bidders. And the bidders—
Even with the subsidy, wouldn't that hold over? Because if I'm not actually committing to a subsidy, once everyone shows up, I wouldn't provide it. I'm just wondering, because in many ways, that's just finding a commitment.
Yeah. Yeah, I agree. Sometimes it's possible to pay a subsidy, sometimes it's not. And you truly see auctioneers giving money to bidders to get them to participate sometimes.
Oh, I completely believe that it exists. It's more that you'd have to be able to commit or else you wouldn't pay them. Okay.
You could, or you could distort actually the auction format where you say that with some probability you will just like sort of run a lottery or something. And that way you reduce the competition in the auction, and maybe that does that too.
If you can commit. So I think to some extent that then goes back to Dan's point. So if you can commit, if you're really thinking that sort of you have the ability to sort of promise utility, right? I think that's like a subsidy. You have the ability to promise utility to the bidders, and then you can get around this. So here the issue is you can't really promise utility. You can't help yourself but to capture this utility from the bidder. I mean, in a sense, it's a hold up problem.
Right?
There's
also another aspect, namely that you basically assume that you need positive X to get any bidders to find out about your auction. Right? It really is that you somehow this is if you would have that there's some minimal X that is always there, for example, or stuff like this, or somehow that it wouldn't kind of go multiplicatively into the number of bidders, into the Poisson thing, then you could also have, right? Because if I'm a buyer and I expect nobody else to turn up, I still really want to turn up, right? As the only one.
Yeah.
So related to this, by the way, so in equilibrium, the seller still makes effort. Is that correct? Like this is the case of no trade, right?
Yeah.
So then what the seller is going to do? The seller is not going to put any effort.
Mm-hmm.
So, but if I'm a buyer, okay, I'm thinking about the seller's deviation, right? So if I believe that the seller is not going to make any effort, and suppose that all of a sudden I got contacted by this guy, so then I believe that I'm the only guy. I'm going to participate.
Yeah, maybe.
So. I mean, I don't understand like how this equilibrium works now.
Yeah, I know. You have to be a little bit more careful than that. Yes, exactly. But so what the statement is, you can't have an equilibrium in which this happens. So you have to sort of set the off-path beliefs correctly. I think you're right.
I see, but so it's still in equilibrium. No, in this equilibrium, the seller makes no effort. So
exactly, the seller makes no effort. You will have some belief about how many other bidders have been contacted if you are contacted. And then it can't be the case that every bidder who has been contacted participates, because that would be self-defeating. It also can't be that no one participates, so that would also be self-defeating. So it will be off-path somewhere in between. And it has to be at that level so that the seller recruits sufficiently many so that really, so it has to be at the 2 or something.
Stephan, maybe just to the same point, isn't sequential approaching for bidders partially relaxes that problem?
Sorry?
So if the seller approaches bidders sequentially.
Yes. So yeah, sure.
That partially relaxes this problem, I guess.
Yes.
It's completely if I can show the number of bidders who already agreed. But here probably everyone agrees up to a certain point.
Yeah, so the idea would be, so there's sort of 2 forms of search, obviously, right? So that you can sort of search people sequentially, one at a time. So I ask you, do you want to buy my house? We bargain, at some point, it breaks down. After that, and only after that, I contact the next person. Okay, that's strict sequential search. I will never talk to 2 people at the same time. Here, the idea is it's strict simultaneously. I will only, contact people at the same time.
No, I was thinking like having the bargaining stage at the end, yes, but the approaching people, soliciting them to participate, being sequential. So once I have a certain number of people on board, I stop searching. because I know that people will reject, and that gives me commitment power because I can show how many people are on board.
Yeah, if you can show this, that's true. But if you cannot show this, so this is a version that we looked at some point. Okay, so basically it gives you perfect control over the number of bidders. That's what.
Yes.
That's the difference. So here you don't have that perfect control.
Stephan, I have a following question. So in your model, discovering V and discovering N are bundled together, right? So you pay one cost to discover both. And basically the breakdown is a holdup that basically you're held up on the C by the seller. I'm wondering which part of the holdup is the important one, because from what your intuitive explanation, it seems that the N part is the one that breaks things down. But I'm also held up on discovering V part. So I don't know. Somehow it would be interesting to see, if you, let's say, separate the two decisions somehow into two different costs, which part is the one that breaks the market?
Okay, you're saying I can pay some money to learn about the value, and I think can pay some money to learn.
For example, because there are two holdups happening at the same time, and both are kind of going in the direction of breaking the market.
Okay, yeah, I'll think about it.
I had a somewhat related thought that for application, you can believe that people learn stuff partially. So, I can enter into the auction a little bit half-assed without being certain about my valuation, but, just knowing that it's above a threshold or even not knowing anything and just, putting a penny to enter. So having sort of more continuous notions of C might soften things up as well.
Yep. So I think there are two parts. So at the end, you said there's a certain continuous. So you could also think about the distribution of C. That's what we do. You could also think that you can bid without paying C and without learning about your value. That would also be interesting. I think we had a version of that as well. So a standard story is, before you, in many settings, you actually have to invest some money to learn. I agree. That would also be interesting. Actually,
again, it depends on the application, and when you don't have one, then it's hard to focus on what the appropriate assumption is.
Right. So here, you have to pay it in order to participate, and that creates a problem. If there are no entry costs, in a sense, there's less of a problem. Okay. Good. Wonderful. So this session is like 50 minutes. Is that right? I guess. Fine. So we had a lot of fun, so that's good.
We still got another, let's say, 10 minutes, just because we started a little late.
Okay, wonderful.
Go for it.
Yeah, no, so perfect. Okay, so so we had an equilibrium. Okay, so this was a proposition for the case in which C is large or lambda B max is smaller than lambda S min, right? So we have market breakdown because the seller can help. So he recruits too many bidders. So now we can look at the other case in which lambda B max is larger than lambda S min, for example, because we pay a subsidy and reduce C or something. Okay, so let's look at lambda B max being larger than lambda S min. So then we can have trade. Okay, so here's the case. Then in this case, there's going to be a cutoff S hat such that the equilibrium with maximal trade will look as follows. So first, if this sampling costs are way too high above the seller's break-even level, the seller will not recruit anyone. So lambda star is equal to C. That's clear. For intermediate solicitation costs between S hat and S max, the seller will recruit some number lambda star at which the marginal cost is equal to marginal benefit, R prime of lambda star equal to S. And every bidder who is contacted is happy to participate. At some point, as S decreases, the bidders will not be happy to participate anymore. So if S is below S hat, lambda star is going to be capped at lambda V max, the bidders break-even level. The bidders are mixing with some probability Q star, at which the equilibrium cost of participation S over Q star is equal to the marginal revenue at lambda B max. Okay, so here's a picture again in blue, the marginal revenue curve, in red, the average revenue curve. If S is above 0.14, the seller recruits no one. If S is below lambda 0.14, the seller recruits at least 2.7 or something, right? Somewhere here on the blue line, for example, at 0.1, the seller will recruit around 3.5. And at some point, the seller will want to recruit more than 5 bidders. Why is 5 important? Well, suppose the entry cost is 0.03, then the bidder's break-even level is exactly at 5. So when the bidder's break-even level is at exactly 5, the seller would recruit too many bidders if he would just recruit everyone and everyone would participate. So it can't be an equilibrium that we have more than 5 bidders participating. So we're going to be capped here. And as S decreases at that point, the bidders will start to mix, and they will mix at exactly at that point that the seller is indifferent, to at that point to increase the number of bidders anymore. Okay, so margin revenue to margin cost at lambda B max.
So
yes?
I have a question. So as S goes to 0,
yes, S goes to 0, yes.
Do you know the number of expected bidders, N or whatever, in the auction?
So the number of expected bidders has to be kept at lambda B max, because
that's the
fixed by the free entry of the bidders, right?
So as S goes to 0, that still it's a fine.
Exactly. So even if S goes to 0, the bidder level is fixed by the free entry condition. Thank you. That was good that you asked. Okay, so so what's interesting about these things? Well, so again, we have an inefficiency. So if S is below S hat, then lambda star, the bidder's participation level is fixed, as Gabor said, by the free entry condition at lambda B max. And the bidder's entry probability Q star is so that the seller's marginal, optimality condition holds. So in particular, the total recruitment cost, so the total waste, if you like, that goes into recruiting bidders is lambda star times S over Q star. That's the cost the seller expends on marketing, lambda star times S over Q star. That's fixed at lambda B max times R prime at lambda B max. And the right side here is independent of S, okay? So whatever is the solicitation cost, so even if the solicitation cost is very small, the seller exerts, a lot of effort into recruiting bidders, but most of this effort is in a sense wasted. Okay, so it's wasted in the sense that the seller would like to commit to recruit only lambda B max bidders. And if he could, then both the bidder and the seller would be better off. Okay, and actually for small s, we would get approximate efficiency. Notice another little thing here, so where things get made interesting, is that the total recruitment costs depend on the marginal revenue of the seller at lambda B max. So if the seller is able to squeeze out more revenue out of the bidders on the margin, that's bad for the seller. It increases the recruitment costs, okay? So this tells you already something about the format and the choice of the format here. So choosing a format at which on the margin your revenue is high from an additional bidder is a bad thing, because it only increases your cost of recruiting bidders without being able to actually increase the number of bidders who are participating, and without actually increasing your revenue because of revenue equivalence. Good. So I already mentioned revenue equivalence. So the result is independent for this simple case with an observable number of bidders of the actual auction. So it would also hold for second price auction, ascending, descending auction, and so on. In fact, this goes a little bit further. So all we needed was sort of the properties of the shape of the R function and the U function. That's what I needed. I needed these properties of the R function, U function. In principle, one could think about a sort of more general bargaining game between the buyers and sellers and make conditions, impose conditions directly on the R and the U, okay? Could also make different assumptions, of course. Ex-ante heterogeneous bidders, so this would be another robustness check. So one could think about heterogeneous entry costs, or the bidders getting some signal ex-ante, okay? So this would make bidders, heterogeneous. So then the nice thing is we get a pure equilibrium. We can't characterize it as nicely anymore, but we get a purification of the equilibrium. You could think about the set bidders, for example, getting a good signal or a bad signal, right? And then only the bidders who get a good signal are entering. And in fact, in this simple example, basically conditional on having a good signal, things will look very much the same as what we just had. Good. So more interesting extensions. In a sense, these are interesting extensions. Revenue equivalence is a bit of black magic. Really, we don't need this. So we can tell you something about what matters in terms of how the rents are split between the buyer and the seller. So the R and the U function tell us how the rents are split. And what's important is if there are more bidders, then more of the rents go to the seller. And in a sense, there's something that's bad about the seller, right? This is limited commitment. Good. So that's some of the extensions. We discussed a little bit about subsidies and entry costs. That's more in the paper. And here are other extensions. So uncertain seller type. So suppose the seller could have either, suppose the seller's cost could be low or high. And naturally, a seller who has a lower sampling cost will recruit more bidders. So what this will mean is that a bidder is uncertain about how many other bidders have been contacted. And I think that's very natural. So it's a very weird fact about equilibrium that I know exactly how many other bidders are contacted. In fact, I would think that I learned something from the fact that I'm contacted, which is the case here. What I learned is that it's very likely that the seller has a low type because the low type samples more bidders, so I'm more likely to be contacted by a low type. That introduces a sampling bias. So condition on being sampled, it's a low type. The low type samples many bidders, so this may make me cautious to enter into the auction. Okay. In fact, if SL is very low, this can lead to the high type being driven out of the market. That's a simple binary case. We can also then think about sort of a continuous distribution of recruitment costs. Seller's recruitment costs, say, uniform on 0 S max. And then look what happens. So, what are the equilibria? Well, it turns out that if the entry costs for the bidders are low enough, in a sense, nothing happens. So Q star is equal to 1. Every bidder who is contacted enters, and all the bidders choose all the sellers choose a positive recruitment level lambda star, at which marginal revenue equal marginal cost. So everything is fine. Above this cutoff, everything breaks down immediately. So Q star is equal to 0. So no bidder enters who is contacted, and all the bidders choose to recruit no one. Okay, except potentially S equal to 0. Okay, so there's complete market unraveling in this case. So either every seller goes in for all levels of cost, or no seller goes in. Okay, and that's because of this sampling bias, which always makes me more pessimistic about the type of the seller. So this is a very extreme form of inefficiencies that happens here. But that's variation number 1. Variation number 2, unobserved participation. So a few of you already said, it's sort of often you will not know how many other bidders there are. So in art auction, there are chandelier bids. The seller can actually make up bids and say, I just saw a really high bid, and you're not actually competing against someone else. You're just competing against the bidder, against the seller. If the bidders do not observe the participation level, then the bidder's behavior will depend only on their belief about how many other bidders there are, but not on the actual number of how many other bidders there are. So by changing the actual number of other bidders, the seller is no longer changing their behavior. And changing the behavior, making bidders more competitive, that was a big chunk of the incentive of the seller to increase the number of bidders, right? And this incentive, making bidders more competitive, that's gone now. So the seller has less incentive to recruit bidders with unobservable participation. And that's actually now interesting because notice that I said before that lower incentives to recruit bidders can be a good thing. So indeed, when the sampling costs are small, the seller's profit is higher with unobservable participation, exactly because of this fact. Otherwise, can be a pretty bad thing. So for intermediate levels of sampling costs, there can be unraveling. The seller recruits a certain, is expected to recruit a certain number of bidders. And then the seller always have an incentive to slightly, cut down the participation level. The bidders anticipate that, they bid less aggressively, the seller has less incentive to recruit bidders, and the whole thing unravels. Okay. Last thing is, there actually is a very robust no trade equilibrium where no bidder participates, is expected to participate. And if a bidder participates, the bidder thinks no one else is there and so bids 0. Okay. So the problem here is the seller cannot commit to recruit enough bidders, sort of the opposite of what we had before. Okay.
So it looks like the revenue equivalence then breaks down, right?
Thanks. Yes, exactly. So with commitment, revenue equivalence holds with unobservable and observable N. I think, Heskey was mentioning this before. But as you said, so without commitment, we don't have revenue equivalence between the first price and second price auction anymore. Okay, because of this difference incentive to affect the bidder's behavior. Okay. So that's one of the interesting things I believe here. Okay, good. Last point, and then we're basically done. Quality uncertainty. I think Eva asked about that. So suppose there is uncertainty about the value of the object. So suppose bidders have common values. Values could be high or low. And suppose bidders observe noisy signals about the quality. So standard conditional IID common value setting. Then, as you know, the main important thing about auctions with common values is the winner's curse. So if I win, that's bad news because the others have low value. And if there are more bidders, the winner's curse is stronger. And the more bidders there are, the more cautious the bids will be. Okay. And so in equilibrium, actually, even if the entry costs are low, we'll have similar results with excessive recruitment. Total recruitment costs are going to be constant in S. Why? Because as the seller recruits more and more bidders, the bidders actually become less and less aggressive in their bidding behavior, because this winner's curse becomes stronger and stronger. Okay. And again, that's sort of an implication of the lack of commitment of the seller. There are some caveats. So what we're really looking here is an auction with an uncertain number of bidders. So bidders compete in a common value auction with an uncertain number of other bidders. And there are some interesting features about these auctions that I look at in another paper. Okay, literature connections. I promised this, but time is running out, I guess. So there's a big literature on auctions with costly entry, and some of you have made contributions to that. So some of this literature looks in particular at optimal auction design with commitment. So an interesting finding is you get first best. And yeah, then there's a result. Then you can look at an informed seller, a seller who knows the value of the object. That's something I do in a paper with Usher, other papers with Usher. And last point, just to mention, I mean, really, this is a model of simultaneous search, right? It's a model of simultaneous search where the searcher decides how many samples to take. And the difference from the standard, the old Burdett and Judd is that we have asymmetric information. That's the first thing. And there are costs of quoting a price. Okay, so someone contacts me, asks, do you want to make me an offer? And I say, well, I don't know. It's really costly for me to make you an offer. And that's actually a case, that's something that happens, every now and then. Good, so there are price quoting costs in a simultaneous search model. That's really what we're doing in terms of search. Good, so that's it. So that was fun. So we looked at an auction with an endogenous participation level, which is jointly determined by the actions of the seller who exerts effort to recruit bidders. So this is marketing or search. And the bidders, there's an entry decision. So bid preparation, evaluation, or costly signal acquisition. Okay. And we've seen how these two things interact, how they can cause inefficiencies because of wasteful recruitment. There's a cycle, the seller recruits more, the bidders become more reluctant to enter. We've seen this can have dramatic effects in terms of market breakdown. We've talked about uncertain seller's costs with a sampling bias, where if I'm sampled, I think this must be a seller who's really sampling many bidders. Okay, and so this makes me cautious. With unobserved participation, there are lower recruitment incentives for the seller, which can be good or bad. It can be good if the problem of the seller is that he would like to commit to a low participation level, but it can also be bad because the seller cannot commit to a lot of participation in order to make people behave competitively. Okay. And last, we talked about quality uncertainty and adverse selection in common value auction. And there we've seen that sort of the winner's curse actually is very similar to a problem of entry. So the more other people there are with an entry model, the more cautious I become to enter the auction. And here in a common value auction, the more other people there are, the more I become, concerned with the winner's curse and the less aggressive I'm bidding. And in fact, these two things work very similar in terms of the outcomes. Okay. So that was fun. Thanks a lot. That was great. I don't know how you do these things. So thanks a lot, that's for sure.
We now open up for questions. So anyone is free to ask. And even after we close formal questions, I generally leave the room open for people who still have more. So first question, feel free to unmute and ask.
Stephan, so of course, obvious question. So have you thought about reserve price?
Yeah. I think the draft, which I haven't posted, has a reserve price. Yes.
So I mean, there must be, if the there must be some relationship between the optimal reserve price with the S, right? This cost.
Yeah.
So is there?
So we don't want to think about as sort of choosing the reserve price. You also have to think about whether you want to make the reserve price public, so then it becomes a signal. But we would just fix the reserve price. We would say, this is just, an expression of the seller's bargaining power, really.
I see. So you didn't characterize the optimal reserve price?
No.
Okay.
So Stephan, I'm trying to get some applied insight from this, and maybe you can help me to do that. I mean, one thing that this group thinks a lot about is, the impact of the internet. So, you know, if I think of the internet as something like making it cheaper to market, you know, reducing these costs, recruitment costs or marketing costs, then what does that do to house prices, right? I mean, that's, you know, if you want me to take that application seriously, does it match up with that? So I'd find it super helpful to have that kind of comparative static in the context of an application to see if it's helping me understand something about observation rather than just the model.
Yeah, I did. So we will.
Stephan?
Yeah.
Can I ask a question?
Yeah.
So pre-COVID time, I was traveling a cruise and they had an auction, art auction. And so the question, the applied question here, how many glasses of free champagne would you give the cruise participants in order to participate in the art auction? And whether you would run a promotion that would say the first 10 would receive a free sample. So the subsidy, but only to the limited number of people.
Okay.
Would that be useful?
That sounds a good idea. Yes. That sounds like a good idea. So yeah, no, I think sort of, so there's a value in a subsidy in terms of helping you to commit. Oh no, in this case, actually, so that was wrong. So it helps bidders sort of to promise bidders some utility from being in your auction, even if you can't help yourself to generate a lot of competition. You're promising, you know, I'm not gonna take everything away from you. That's the important part here. In terms of sort of, I don't know, applications. So actually art auctions are interesting because there's a big difference between the US and Europe, I think, in terms of whether you're allowed to make up competing bids. So, so I forgot, but I think in the US, it's called sales talk. You can sort of make up the presence of other buyers to some extent. You can pretend even if you're selling a company. Okay, so when things get a bit, you know, millions of dollars, billions of dollars, you can sort of imply that there are other bidders to a large degree. In Europe, that's actually not allowed. They will be more, you know, critical in court. So that's my understanding. You know, there's this book, Negotiate Auctions, and that's sort of one of those things. And you could ask, is it a good thing or a bad thing if you allow sellers to make up the presence of other bidders? So conversely, do you want to help sellers to commit to credibly reveal the number of bidders? So make the bidders observable or unobservable. Okay. And that's sort of, you know, for example, in art auctions, there are these chandelier bids, which I already mentioned before, which sort of have some special status, and there are actually court decisions around these things.
I'm going to shut off the recording now, but if anyone has any further questions, feel free to ask.